Hi everyone, today we'll go over chapter 14, sampling, variation and quality, or in general we can say control charts. Let's see what control charts are. The topic you learned earlier in the past few weeks goes around the fact that data have variation, and because of that variation, managers, when they want to make decisions, they have a lot of challenges, because when you make a decision based on an average, it's very important to know, is that decision based on average going to cover all of the possible things that are going to happen in the future? Is that going to put everything under cover? So that's the main question here. And in this chapter, we're going to find a method that creates a lower bound and upper bound around our dataset, and making sure that our process, our decision for the process or for the organization is actually creating a controlled system. And what we mean by that, so for example, if you want to make a decision with 95% accuracy, that decision should work among every 100 cases. 95 of them should be covered by our decision. No mistakes, no errors involved there. 5%, up to 5% is okay. More than 5% or equal to 5% is not okay. So if we are covering 95 or more than 95% of our cases, our system is in control. If we are not covering 95% of our cases, the system is not in control. So the main problem here is the variation, and that's what we need to understand, that variation causes error, and the decision making including error is a problem that we try to avoid. Okay, so there are two possible errors in decision making, and one is stopping a properly functioning process, and also failing to detect a malfunction of the process. Put it in a different way of saying is that if a system is working properly, is working well, and because of data analysis that is being done by mistake or having some errors, we consider that system is not working properly. So system is working properly, but based on our research, based on our data analysis, we decide that the system is not working properly and we stop the system. So that's an error, right? So that's one type of error. So one type of error in decision making is the system is actually working well, but our decision is saying that the system is not working well, so we need to stop it. That's an error, right? That's an error in decision making. And you have seen it in your life, in your work, even in your personal life, in families. Someone is doing the right thing, but because of a misunderstanding, which is coming from data, right? Interpreting the information was not done correctly. They say, no, stop doing that. But actually it was a right things to do. The second type of error in decision making is there is a problem in the system, there is an error in the process, in the system, and we don't detect it. Again, because of wrong data analysis, could be because of some data collection problems, and we fail to stop the system that is not working properly. That is another type of error. So we have two types of error. A system is working well and we stop it. Second error in decision making is a system is not working well and we let it go and let it continue to work. sampling distribution of the mean. So what is sampling distribution of the mean? We need to understand that there is a high variation in real data. When you get the real data and you graph the process, for example through time, especially in time series, there is a high variation in, when I say variation, I mean changes. For example, let's talk about sales, right? If actual sales in one morning can be very low, and right after 11 it can be very high for day 1. For day 2, for some reason, maybe the first hours you have a high volume of sales, and then at 11 that reduces from the other day. And these changes actually create a higher level of error in decision making. So what do? For example, we collect data for each day 3 times, and these 3 times we can get the average of it instead of using all 3 values from the day. And in this way, high variation in actual data reduces because we get the average of each day, right? So averaging is one of the methods that we can use to smooth our data. So this process is called smoothing process. So smoothing process is required because when you want to make a good decision, that actually put your data in a smaller form of data. So another thing is sampling distribution of the mean. So if I get the average of each day, and each day has 3 samples, 3 records, so I have actually created a sampling distribution of the mean, and my sample size is 3 because I get the average of 3 values per day, right? If I do it per week, if I have like 1 year data, and that's too much data, too much variation, I get the average of the week, and for 1 week we have like 21 data, right? Then sample size is 21. So you can see that this is like a high variation here. There's a high variation from lowest values to highest values. But if I get the average of each day or each week, right, or each month, it gives me an approximately normalized data. So what do we do with sampling distribution of the mean? We actually normalize the data that are not normal. So these data are not normal. They're not like a bell shape. Why do we want bell shape? If you remember from previous topics, we want a bell shape because majority of data are near average, and because we make decision based on average, we want all of our, or majority of our cases be around average, so that when we make a decision based on average, it covers majority of our cases. Okay, so if I make a decision based on average here, it's going to cover up to maybe 2-3 standard deviation around it, but what happens to the rest? They are outside my decision. My decision is not going to work for these that are far from the average. But if I normalize data by getting averages, or in other words, by smoothing our data, I can normalize the data. Majority of values are around average, and my decision based on average is going to work for majority of them. Does that make sense? Okay, so that's mainly what we do in sampling distribution of the mean. Benefits of averaging: the sample-to-sample variance among mean Hall scores is smaller than the variance among individual Hall scores. Distribution of mean Hall scores appears more bell-shaped than the distribution of individual Hall scores. And that's what I just said. I just said it in a different way, okay? Normal models. So another thing that is good when you normalize your data is that you can use any formulas, any rules, and any statistical decision-making processes that requires normally distributed data. So when you have a normally distributed data, you have a lot of tools that they require normality of data, and now they can be applied. If you don't have a normalized data, you cannot use those methods because those methods require normally distributed data. So sample means are normally distributed if the individual values are normally distributed. Sample means are normally distributed because of the central limit theorem. Hopefully you remember that from Stat 1 or basic statistics. Right? So what does that say in general? In general it says a measure of the sample-to-sample variability in sample means, and it calculates your standard deviation. So in general I can say the average of your averages, right, is actually the same as average of your original data. So your average is not changing, and that's a good thing. We normalized our original data without changing the actual average, and that's a good thing for us. Okay. The second thing is the standard deviation is actually reduced. Of course, the original data was spread, right? Spread, that means average distance from the mean was very wide. Now it has reduced. How much? This is the amount. Your new standard deviation is actual standard deviation of the data divided by radical n, a square root of your sample size, a square root of sample size. How much? That range was large, right? It was high variation. Now it has reduced. How much? This amount. You divide it by radical n. So these calculations actually are not really tough for us because everything is going to be done by jump. Okay, but I believe that when you start operations management, there probably you have calculations. For my classes, I did that. I asked the students to calculate because they need to understand a lot of things, and then they could use jump to find the answers as well. But it really depends on how the course is designed in your next class. So let's move on and go to the point of, so here is what we can say. This is a normalized data. Average is the same. This is the population's average. What's the standard deviation? Standard deviation is the sigma divided by radical n, and this is variance. We show normal distribution by variance, not by standard deviation. And if you remember, I said variance is a standard deviation to power 2 or a square, right? So this is variance divided by n. The radical is gone because it's squared. So next is, what are the control limits? If I want to put you back on what actually control limits are, I need to remind you of confidence interval when you learn confidence interval topic in basic statistics. So if you want to cover 95% of your data, and you also learned one more thing in the past week, and that was the topic of a standard deviation. So you learned that 2 times standard deviation covers almost 95% of your observation. Do you remember that? So that's an important thing that you learn. 1 time, 68% approximately. 3 times, it covers 99.7%. Okay, so here's exactly the same. We're trying to find what range or what percent of our observation or future things that are going to happen are going to be covered in our decision making. If you want 95%, you need to use 2 times standard deviation. If you want to cover 99.7%, you need to use 3 times standard deviation. So how do you know which one to choose? Your question will always tell you. Your question is always going to tell you, or your manager is going to tell you, or a rule is given to you that we want to go with this much accuracy. So how does that work? So what is the control limit? The boundaries that determine whether a process is out of control or should be allowed to continue, right? So we create that range around our data set. There are upper bound, lower bound. What's the worst case scenario on the top and on the bottom? And if we say we want to cover 95%, right? We use 2 standard deviation around average. That's it. And then find the upper bound and lower bound and make our decision based on that upper bound and lower bound. So what's the formula? The formula is, that's a symmetrical interval denoted as. So what is XBAR? XBAR, if you remember, is your average. Average, for example, we got average of each week, right? So if you have 52 weeks in 1 year of data, for each week you got one average. Week 1, average 1. Week 2, average 2. Week 3, average 3. Up to 52 weeks, right? So what is the average of all these 52 weeks? That's your XBAR. That's your XBAR. So XBAR is in fact the average of all of these averages, which is equal to actual average of your original data. Okay, so where is the upper bound and lower bound? So that's your population average, population mean, plus L. What is L? If 95%, 2 times the standard deviation. If 99.7%, 3 times standard deviation. If the question asks you, it's not very important, we can have much more error, 1 time standard deviation. But for business and for social sciences, we normally use 95%, which is 2 times standard deviation. Otherwise, we will let you know. We will tell you how many standard deviations. Okay. So this is actually, if you have learned standard deviation topic, that's why I said it's very important. You're going to need it for the whole semester and for other courses, including finance, operations management, and project management, few finance courses. So you're going to need this for some time. Okay. So what is mu plus L? Mu plus L is, so this is mu, right? So mu means population mean. XBAR is the average of averages, or XBAR or XBAR bar. Upper control limit, UCL. You will see on exam questions, this one or next one. Upper control limit means UCL. Is mu plus L. And what's your lower bound? Lower bound is mu minus L. What is L? How many times of a standard deviation? How many times of standard deviation? Why do we use how many times of standard deviation? Because we want to see what portion of data, what portion of observations should be covered, right? Type 1 and type 2 errors in control limits is exactly the same as decision error that I started the topic with. So if you remember, when I started the topic, I said if a system is working well and you stop it, that's an error in decision, right? So look, type 1 error. The mistake of taking action when no action is needed. Taking action means changing a system that is working correctly. The system is working properly, correctly. The system is in control, right? All of those cases are taken care of, but we make a decision that it's wrong, it's not working properly, and we stop it or we change the process. That's type 1 error. What's the type 2 error? The type 2 error is the mistake of failing to take action when needed. A system is having a problem, is not covering all cases, not solving all problems, is not producing the amount that is required, is not selling as much as it's required, but what's happening is we are letting it continue to work, and that's the second type of error. You just need to recognize the difference, and that charts explain the same thing. So read the book on that. It's actually very simple to understand. Okay, so let's move on. So these are topics you will read from the book. And this is a good example of control charts. Let me see if I can bring this down, and maybe I can zoom in. Okay, look, these are the actual data. These can be different days. So we have 10 days, right? Each day we collect samples. How many? Like 1, 2, 3, 4, 5, and 6 here. Maybe 11 on day 1, maybe 11 on day 2. And you can see day by day they're changing, right? They're changing up and down, up and down. So this is a high level of variation. If you want to make decision based on this high variation, the black dots, it's not appropriate. It's not going to give you a good decision making. So what do? We get the average of day 1. We put a point here. Average of day 2, average of day 3, average of day 4, average of day 5, and so on. And what do? We connect them. And that creates a chart for us. At the same time, we find, let's say we want to go with 99%, right? For 99%, how many standard deviation do we use? 3. 99.7%, right? 3 standard deviations. So 3 standard deviation approximately is going to cover that upper bound and lower bound. Now, if all of these points of averages that we calculated are in between the upper bound and lower bound, we can say this system is in control. That means the decision we make is going to be covered in that range. If any of these points, points of this line falls on the control limit, upper and lower bound, or outside of it, on or outside, we say the system is out of control. That means we need to correct our decision. We have to find out what is the cause of these changes that making this system go out of control, and make sure that the system is back to control. Why do we need the system to be in control? Again, for decision making, too much variation is not good. We need to reduce the amount of variation so our decision works for majority of cases. And this is, again, smoothing your data or normalizing your data. Original data, high variation. Do you see that? There's a high variation in your original data. But when you get the averages, it reduced it and put it into those bounds that we create. Right? So, okay, so another example of an XBAR chart. Why do we call this XBAR chart? Because the chart is created by adding and subtracting the 2 times or 3 times of standard deviation on XBAR, on the average. It's average plus minus some multiple of some coefficients of standard deviation. Do we have other types of charts? Yes, I will talk about that later. Especially in operations management, you will learn more about that. Not in this class actually. So this is an example of a case that is out of control, right? So you can zoom in and you can see that in this case, one point is not only hit the upper bound, it's also go a little higher. That means the system is out of control. Okay. Okay, so I think it's a good time for us to check an example on JMP, and to do that, let me show you the formula as well. And this formula is actually the same formula as what you learn in confidence interval, if you remember. If you have a normal distributed data, you had average plus minus z. Z is actually the z value that tells you how many standard deviation you are away from the mean, right? Times sigma over radical n. If you go back to basic statistics, you must probably remember this number right here. Okay, so what is S chart and what is R chart? So S chart, so the first one you learned was XBAR chart. This is S chart. S chart tracks the standard deviation S from sample to sample. So it's showing, instead of showing the changes of average, it's showing the changes of standard deviation, which shows variation. What is R chart? Another factor to recognize variation changes is range. Range tells you what are the changes per day. Is it too much change for that day or less changes for that day? So it tracks the range rather than the standard deviation from sample to sample. Under data, so we go to files, we go to data, and under data you can see control charts.jump.
So supposed to be days, Professor.
Yeah, sorry. Where is that? So one more time, we go to quality and process and control chart, XBAR chart, and days. Oh, data goes to Y, right? And days go to the subgroup. That's what we did, right? And that creates our control chart. So what are we looking for here? What are the things we should look for? You can actually change the way it looks like. You can extend it, you can drag it down, make it larger, make this graph larger. And we just, for this course, we just look at the XBAR chart. But remember that the actual decision in real work, you need to use both R chart and XBAR chart together. Okay. Okay, so here you can see that your upper bound, that's your upper bound, that's your lower bound. And these are the average of each day. And one of the days is outside the control limit. So this system is out of control. This system is out of control. Do you think we can find upper bound and lower bound? Do you see them here? It's right here. The UCL, right, 160. LCL, 142.8. And average is 151.5. Everything is right in that. Previously, it used to be like everything was on the chart. You could see numbers on the chart. But that upper bound is 160. That lower bound here is 142.8. And that average, that green color, is 151.5. So on our exams, when I give you the data, you are supposed to create that chart. And one of the questions will ask you what's the upper bound, what's the upper control limit. You just take it from there, the first one. The other question might ask you what's the lower bound, 142. I will not ask about range, right? Why is that 0? Normally when one of those values is negative, we push it up to 0 because negative values doesn't have a meaning in this case. For example, for sales, it doesn't have a meaning, so the system push it up to 0. So once again, we went over what is IV and what is DV, independent variable, dependent variable. Don't forget that put independent variable in X on jump, and dependent variable goes to Y. Don't forget we have two types of statistics: descriptive, describing data or graphing and explaining data. Inferential is generalizing, and the best example is hypothesis testing. Types of variables: qualitative and quantitative. categorical, non-numeric, like color and gender. So this is the type of variable, and quantitative is numeric. Generally, we use continuous variables in this course, but if you want to work with discrete variables, those are the ones that you cannot write them with the decimals. You cannot write them with decimals. Level of measurements, again, categorical variables, ordinal, nominal. Nominal is a groups that these groups cannot be ranked, like gender. Ordinal are the ones that you can rank them, like education level. Continuous variables are into two parts, ratio or interval. Ratio when 0 has a meaning or 0 is an option. If 0 is not an option, that's interval. So what do we do on descriptive statistics, descriptive data? So if you have categorical variables, what do we do? Frequency table, bar chart, pie chart. Where do we get those on JMP? On JMP, I wrote it here for you. JMP, go to graph, chart, options, right? I think this actually has changed in our current JMP. JMP has changed this one. So let me show you. If you had, you wanted to do a graph, so let me open the company's data maybe. You have company's data with the no outliers. We just did it last week. That's the data, right? Those red ones are the categorical, blue ones are continuous. So I go to graph, I go to, so previously it was different, so they changed it. Now we have legacy and we have chart. So we go to graph, this is for categorical variables. Graph, legacy, chart. And I can create a, so if the variable I'm interested to analyze is size of company, I just drag and drop it into categories. And I can change bar, pie, and other type of charts. Click OK. And that gives me this information. You want to add labels, just right click, probably on the bar, label, labels, right? Label by value or percent. You can also change this to pie chart, I think, and you should go to, you can also just do that from the beginning, go to graph and legacy and chart, and just change this to a pie chart and drag and drop size here into groups because we have categories, right? That's a pie chart. Right click, you can add labels to it, pie, label, like percent. I would do percent, you can do whatever the question is asking. Okay. What else can we do? Frequency table, right? Go to analyze this distribution. So this is distribution is for descriptive statistics. Alright, so size goes to Y. Anything you want to do for descriptive statistics goes to Y. Click OK. So a histogram doesn't have a meaning for this, so you can remove it or you can ignore it. But here's your frequency table. Counts how many big companies do we have, how many medium companies do we have, how many small companies do we have. And here we also have the probability or percentages. You multiply these numbers. These are actually the relative frequency values. You multiply it by 100, that's a percent. So that's 24.1%, 24.1%, 51.7%. Total is 100%. Okay, so that was this part. So in fact, here when I say go to JMP graph, I should say legacy here. Legacy. And where did I put it? Okay. And then go to chart and then bar or pie chart. Continuous variables, you do histogram, mean, median, mode, right? Where is that? That's actually here. So, for example, sales is numerical. Number of employees is numerical, right? So go to analyze this distribution. And if the question asks you to find average of sales, standard deviation of sales, whatever about sales, about a numerical data. Just drag and drop it into that Y columns, click OK. You actually have a video on this as well. That's the histogram you can check, and you can make it vertical by going. So remember, anytime you want to make changes, you just go to the red triangle, histogram options, and I want it to be like that. You have your box plot, you have your max, mean, median, quartile, the 75% quantile or Q3, Q1, you have mean, standard deviation, and you can also add information by going to customize summary statistics and add, for example, skewness, right? Just go there and add it. You want CV, you want max, mean, median, mode, whatever, range, whatever you need, you just need to go there, and variance, sum. Just click OK, and look, that 95% is your confidence level. 95%, right? It's using 2 times standard deviation for these numbers. All of them are actually added here, and you can check on your question with the numbers here, the one that is the closest, check it, that would be your answer. Okay, that was distribution. What else do we have here? Interpretation of standard deviation. I told you 68% one time standard deviation plus minus average, 95% 2 times. So I might give you the range and ask you what percent is that. So you need to calculate all 3 and see which one matches with the number on here. So where do you get the mean? If I don't give you the mean and standard deviation, you just go to analyze distribution and drag and drop, for example, sales, and both average and standard deviation are right here. Just mean plus 1 time and minus 1 time of 2,621. That's 68%. 2 times of this, which is 5,242, plus minus the mean, that's 95%, right? Just calculate the numbers and see which answer is the correct answer. What else do we have? Let me go back here. What else do we have here? So remember, the calculation of the range is expected, okay? Association between categorical variables, or the chi-square test. That's what we did last time, and you actually have a recorded video on this. So I'll be quick on that. Where do I get my analysis of association between categorical variables? Which are the categorical variables? These are the ones. On exam, I will tell you which one is IV, which one is DV. So just go to analyze. Whenever you have one-on-one analysis, fit y by x, and IV goes to x, DV goes to y. That's all. Click OK. The first thing you see will be a chart. That's your mosaic chart. If there's a question, you can see it and answer it. These are all of your contingency values. And if you don't see expected value, click here. It adds at the end of each cell. What else do we want? Chi-square value, or Pearson chi-square, is down here. Pearson chi-square, 10.076. So that value might be asked. And the p-value is important. Is that less than 0.05? If yes, there is association. Rejecting HO, there is association. If equal or more than 0.05 or 5%, there is no significant association. Right? So these are the numbers I will ask you. This number, and do you reject HO or do you fail to reject HO? If this number is below, if p-value is below 0.05, you will reject HO. Right? And that means, if you reject HO, that means there is a significant association. That's it. And you remember how to create a Cramer's V, right? Cramer's V, you use that formula, just plug in the chi-square you got from here, and divide by sample size times the minimum of number of rows and number of columns. And here, number of rows is 2, columns is 3. Between 2 and 3, which one is lower? This one, -1, multiplied by sample size. What else do we have? So that was here. So when you create the Cramer's V, remember that if it's close to 0, that's a weak relation. If it's close to 0.5 or in this range, moderate. If it's close to 1, strong relation. I gave you a 5 scale, so it doesn't really matter. Control limits, we just did it today. So XBAR is between population mean plus Z, or how many times of standard deviation, minus Z times how many times of standard deviation. So since we did it today, so ignore this part. Do not, let me white it so you don't see it. Okay, so we don't have that. Okay, so go to analyze, quality and process, control chart, XBAR, and XBAR chart, of course. It has changed, the jump has changed a lot, so this is quite old. Data goes to the process. Right now it's Y. Previously its name was process. And day goes to the day goes to sample label previously. Now what's its name now? Let me find it. Subgroup, yes. So let me change that to subgroup. Thank you. So check the XBAR, check your XBAR, and uncheck R and S. So we don't use R bar, R chart and S chart here. Okay, we just use XBAR chart. Parameter, oh, sigma, how many times sigma we need? Let me show you this one. I think I did not show you this one. So let me open the control charts. This is your control chart, right? So for the control chart, if you want to change the how many times the standard deviation is added or subtracted, instead of control chart, you will go to legacy control charts. And legacy control charts, you go to XBAR. And in fact, legacy control chart is actually includes the control charts, XBAR control chart. So you don't need it. So you can uncheck this R or S. You just need the XBAR. How many sigma? Sigma is the standard deviation. How many sigma? Right now is 3, which is 99.7%. On the exam, I might ask you use 2, 2.5, 3, 3.5, 4 to get results. So my data goes to the process. My days go to by or sample label, sorry. Okay. And that's actually what we have here on the text. You can see it says control chart XBAR Y or process, right? Days go to subgroup or sample label. So let me just correct this. So sample label or subgroup. And then so how many sigma? It's right here. You change it. If I say 2.5, you just change it to 2.5 here. And that's it. I think that's just all we have to do. And you get that graph that we had it. So you can see that we have actually all those numbers on the chart. All those numbers, same numbers that we saw on the example, and still out of control. You want to see that specific point up there to see if it's in range or not. You can see it, right? Or you can put your cursor here. It shows you what actual value is and which day it is, and you can compare it. Okay, so I think we are good with this. And what else do we have? So ignore this. This is I used to teach this using Microsoft Excel as well, so ignore this part. It's not. Association between quantitative variables. So that was really quick. So what do we start with? We start with scatter plot. Again, we are doing a one-on-one IV goes to X, DV goes to Y. Let's say we want to see if number of employees have effect on sales. So number of employees, IV goes to X, the other goes to Y. Click OK. That's your scatter plot. Now you want correlation value or R-square value. Go to red triangle, summary statistics, gives you correlation, 0.711. Is it significant? Yes. What else can I add? I can add the fit line, equation of the line. That's right here. Says equal to, that's your intercept, that's your slope, it's the number of employees. How do we interpret this? Estimation of sales when there is a change in number of employees. You took a note on that before, right? So it's actually written on the paper as well. So what else do we have here? R-square is very important. Multiply it by 100. That percent of variation in DV, sales, is explained by variation in employee, number of employee, which is your IV. And so let me just really quick. So you just go to analyze, IV goes to X, DV goes to Y, all those numbers come out. Don't forget to click on the red triangle to take the numbers out. So all of the things I said is right here. Scatter plot, and I showed where to go. Scatter plot matrix, you don't need this at this point, this is for the future. So I made this no color. Multivariate, you actually don't need this at this point. R-square, how to interpret it? Multiply by 100, right? And the percent of variation in DV, just find the name of the DV, explained by variation in IV. That's the interpretation. What about R value? R is between -1 and 1. If it's close to 1, very strong or strong. Close to 0.5, moderate. Close to 0, weak or very weak. And the last part, that's the equation of your regression line. DV, in this case was sales, equal to intercept, whatever it is, plus the slope times independent variable. How do we interpret this? We say estimation of changes in DV when there is a change in IV. Residuals and residuals are not for this exam, it's going to be for the future. Okay, so down here I put a disclaimer, right? Important disclaimer. Dear student, review session and review pages for exams are provided to help the students prepare for exam. There is not enough time to reteach all topics again, solve problems in detail during a review session, and only important topics, formulas with higher chance of being on exam equations are discussed. The instructor keeps the right to give questions from any topic taught during the semester before exam, whether discussed during a review session or not. Make sense? But